Hey guys, you're watching Python tutorial videos on my YouTube channel, Python for Microscopists. In the last couple of tutorials, we talked about loss functions and optimizers, and in this tutorial, let's talk about metrics that we use in deep learning. Again, I'm not going to cover a lot of metrics, but the most common ones that we use. And when I say metrics, this is exactly what I mean. When you do model.compile, loss optimizer is what we covered in the last two tutorials, and today in this video I'm going to talk about metrics. Okay, and in this example we're using accuracy. Now it's self-evident, that's why this will be a rather short video, but in Keras, especially if you're using this, it allows to monitor certain metrics, okay, as we are training the model. Now metrics are recorded after each epoch during the training process, and loss function can also be used as a metric. For example, for regression problems, you can use mean squared error or mean squared logarithmic error, one of these, and that can also be a metric. Okay, because you're after all using a loss function or trying to minimize the loss function. So by monitoring loss function, you can actually use that as one of your metrics. Okay, now if you use a validation data set, for example, if you have a training data set and a validation data set, then whatever the metric, like accuracy, for example, can be calculated for both of these. So you can see, are you overfitting? Because if the accuracy is very high for your training data set but low for validation, that means you're kind of overfitting your model. So then you can take appropriate actions. Okay. Now some of the metrics, again, I listed out here, regression metrics, and in the parenthesis here, this is how you kind of define it as part of your Keras model.compile. MSE for mean squared error, mean absolute error, absolute percentage error, and most of these are self-evident. Cosine, proximity, mean squared, and although I should mention for most regression metrics, it's MSE that's commonly used. Now classification metrics, I didn't put anything in the parenthesis because that would make my slide very, or that would make the font very small, but think of binary accuracy. The way you define that in your model.compile is just binary underscore accuracy, all lowercase. Okay, so binary, categorical accuracy, sparse, and so on. And to be frank with you, most of the time I have defined it just by typing accuracy, just like I did right here. Okay, and this is a built-in function that's commonly used in Keras especially. Now I would like to show you a few lines of code applying both, for example, mean squared error. Actually, let's plot a few of these, and also for classification metrics. Okay, so let's jump into our Spider IDE, and here is a few lines of code. Now, so this part, I'm trying to demonstrate the regression metrics. And all I'm doing is just a very simple straight line. Create an array of values 1, 2, 3, 4, 5 all the way to 10. That's it. This is my input data. If you want, you can just test it on any type of values. And then my model is basically I'm using sequential method to add my model. And the first layer is dense, and the second layer is also dense with a value of 1 because it's just outputting a single value. Okay, and I'm compiling this using a mean squared error, again, a regression type of problem. So mean squared error, my optimizer is Adam. We talked about what it is again in the last tutorial. And the metrics to monitor, you can give multiple, by the way. So I'm defining them as MSE, MAE, MAPE, and so on. And then we are just doing model.fit. In the next tutorial, I'm going to talk about what our batch size means. Okay, so let's save that for now. But you probably know what epochs is. Again, I'm going to talk about it pretty soon in the next tutorial. But this is basically the number of times you're actually doing this, going through all of the data at least once forward and once backward in your if it is a back propagation. And we are just doing fitting x to x itself, okay, the same data. And then I'm just plotting mean squared error and everything. Remember, here I'm just giving these as MSE, but I'm printing this as mean squared error. Now, I believe if you use a newer version of Python, then it may throw some error saying that, hey, mean squared error, you never told me what it is, then change this to MSE, okay? Just giving you a heads up. Okay, let's go ahead and plot all of these. So now, how many epochs did we say? 500 epochs. So this should actually go through all of these 500 epochs. It's just very simple data set. And here I should have added a label, but the first, the green one is, I thought I added a label. Sorry about that. The green one is your mean squared error, or plot one at a time. I'm absolutely sorry about just doing this one. So let's go ahead and plot this one first. You see, this is your mean squared error, and mean absolute error, it shows up in the same color is this one. So it's actually along the same lines. Mean squared error is up here. Now, what am I trying to prove by showing you this? Nothing right now. Put real data. I'll share this code. Go ahead and change your x to whatever your real x value is, and then just keep track of these metrics and see how these metrics kind of compare to each other. Okay, so that's the point over there. And now this bottom part, again, I got this code just by browsing, reading some blogs in terms of generating this synthetic code. So here, for the classification problem, I do not want to use a simple, like x and y. I can, but in this case, I'm actually generating some artificial data by using scikit-learn's make blobs data sets. Okay, with this, you can actually tell how many samples you want and how many clusters or centers around which you're generating these, and how many features, and what is the cluster standard deviation. So by keeping a lower standard deviation, all of these clusters are kind of overlapping, making this a challenging problem, which is okay. Again, a good way of testing these things. So let me comment this part out. I wrote these extra lines to show you how it looks like, but this is the actual part of the code we are trying to use, which is basically the same thing, except I'm encoding, or one-hot encoding our y values to categorical y. Why? Again, because we need to convert them from integers to some sort of a labels or binary classes. So that's what I'm trying to use this. And model, again, keep it very simple. I'm using dense layers. 50, and then input dimensions is 2, right? We have x and y, and my activation function, I'm going to use ReLU, and you need to initialize your kernel. I'm going to use he uniform, which is very common, and the output is going to be 3 outputs because we have 3 clusters here. Okay, and the activation function is, again, try. This is a great piece of code to try different activations, for example, and see how the output looks like. So please try to educate yourself by writing little snippets of code like this, or copying little snippets of code like this if you can find it online. I'm going to share this with you so you don't have to search for it. So now I'm going to do model.compile. When I found this snippets of code online, they were originally using a stochastic gradient descent with a learning rate of 0.01 and momentum of 0.9. Remember the momentum I talked about in my previous tutorial? Here you can actually change the momentum and see how things are optimizing. Okay, so that's why I'm leaving this as commented. If you want, you can change it. Now, where would that go? As part of your optimizer, here I'm using Adam, but instead of Adam, just type OPT. Well, obviously remove the quotes, but type OPT and you're all set. Okay, and since this is a multi-class problem, I'm going to use categorical cross entropy. Okay, and the metrics I'm going to track are accuracy. The whole point of this tutorial is just metrics. In this case, I'm just plotting the accuracy. Again, the accuracy needs to improve as the epochs goes by. So let's actually look at that. And let's actually, yeah, I think that should pretty much do. And model.fit is, we are doing it for 100 epochs, and let's take a batch size of 32. Because we have 1,000 samples, batch size of 32 means 1,000 divided by 32, that many iterations. Again, stay tuned for the next tutorial where I talk about exactly this. And then let's just go ahead and plot the accuracy. Okay, so let's run these lines and see how the output looks like. Okay, there you go, it's done. So now, as you can see, the accuracy was pretty bad. And then it started improving, and then at about, like, for example, 25-ish or so epochs or 30 epochs, now it's flattening out, right? So no matter how much I spend in terms of computing time, I'll probably asymptotically, reach a value of about 83%. You see, 82.6% or so. Now you can improve this, using more training data, or changing your learning rate, for example. and all that stuff. This is fun stuff if you are really trying to learn how the learning rate is going to affect, how momentum is going to affect. So I'll leave this to you, use stochastic gradient descent or some other function. I mean, even for optimizer, Adam, try to define your learning rates, try to change the default learning rates and see how things perform. Okay, so I hope you learned something, again, as usual, from this tutorial, and please subscribe to this channel. In the next tutorial, let's talk about one more aspect of this, which is batch size and epochs. Okay, so thank you very much, and let's meet again in the next tutorial.